organized. Testing. That's not working, is it? That one works. All right. Just forgetting that, I'll just stay close to the lectern. Right. Let's maybe start with a little bit of fun. Yeah. Right. Let's try and turn the lights up a bit. Okay, so we'll find out, I guess, in the next couple of weeks we're going to talk a little bit about what some of these images might mean. And I don't know whether any of you recognize this as one of the first images from the James Webb Space Telescope, which has just gone up. And is kind of the next generation to the Hubble telescope, which maybe you've heard of. We're going to be talking about lots of these things a little bit more in the next couple of weeks. So before we get on to any of that stuff, what I wanted to do is just to kind of briefly show you our Canvas page and kind of talk you through where you can find stuff there. So probably it wants me to. Okay. Right, hopefully you guys are old hands at navigating through Canvas now, but you can find just about everything that you need to, hopefully, on here. So I'm David Ponton, I am the course coordinator, and I'm also going to be teaching the first 2 weeks and the last 2 weeks of semester, and then a couple of my colleagues are going to be coming in and teaching some of the other topics as well. And between us, we'll kind of lead you through a bunch of different physics topics. And you can find out lots of information about the course and get to all of the material through this Canvas site. So here we'll put on announcements about what's happening during the week. And then if you go and you look, for example, at the modules section, then you can find all of the materials for the different weeks as we go through and look at what the topics are going to be that are coming up. Again, if we go back to the home, you'll see a link to the course outline that has all of the kind of most important details about the course on there. We've also can find out how you can get in touch with us. And also down the bottom of here, there's like a little welcome video which has a little bit of an introduction, but basically contains the same information as is in the course outline. So the way that the course is set up is that we're going to be having lectures each week, which are going to be covering going through the material. There's then an associated problem sheet that you guys will work through in the tutorial classes. Now, because the tutorial classes happen throughout the week, the tutorial actually comes the week after the lectures, so therefore there's no tutorials this week. There's also no labs this week, but next week we'll be doing the first problem sheet in the first tutorial class, which will cover the material that we do in the lectures this week, and so on. So that will follow on through the semester. There's also a quiz for you to do. The quizzes are a great way to bank some marks. You can repeat the quiz as many times as you want until you get an answer, until you get a score that you're happy with. And so that's lots of practice problems, so make sure you do the quizzes as well. Again, they happen the week after the corresponding lecture material, and so the quiz for this week's lecture material will be due by the end of next week. Again, lots of details on Canvas. If you have trouble with navigating or finding things or figuring out what you have to do and when, then do get in touch with me or one of the other lecturers. Like I said, there are no lab classes this week, but there is an online safety induction that you need to do. You won't be able to come into the lab classes until you've done the online safety induction, so please go ahead and do that. Again, the labs are hopefully a good way to kind of bank some points, get yourself on a good score leading up to things like tests and exams, and are hopefully also fun as well. So the labs, again, no labs this week, but do go on and do the safety induction and look at the information about lab stuff that you find in the modules pages there. What else do I want to say? We have a course textbook. There is information about what the course textbook is, again on Canvas or on that welcome video. It's not necessary to buy the course textbook. You can access a copy of the course textbook, either physical or electronic, through the library, so you can get to it through the library website. But there is information if you do want to get your own copy for whatever reason, then there's information about how you can do that here. We're going to be providing lecture notes, so that, again, it's not kind of essential to work from the course textbook, but it does have lots of extra examples because, usually with a topic like physics, you kind of learn or figure out what you know and what you don't know by working on problems. So it's a great source of extra problems, basically, and obviously can give some alternative explanations of things as well. Right, so that's it for a brief introduction, I guess. And so if we now move on to what we're actually going to be talking about in these first 2 weeks, we're going to be covering two topics. We're going to be talking this week about particle physics and the next week about cosmology. Now, these seem kind of topics that are almost at the opposite end of the scale. We're really going to be talking about some of the big ideas, the big questions in physics. And so, particle physics deals with what are we made from, or what is everything made from, and what are the kind of fundamental building blocks of everything that we see in the universe, and how is that related to the forces between them, and so on. So particle physics is really dealing with the smallest objects, in kind of indivisible objects in the universe. On the other hand, cosmology, that we're going to be talking about next week, well, that deals with kind of big questions like how did the universe start, how might the universe end, how does how does it work in general? So where did we come from on a kind of cosmic scale? So this is dealing with, well, not even the largest objects in the universe, but just the universe as a whole. So these seem like slightly strange topics to put together, but we're going to see as we go through that actually the two are kind of intimately related. So this week is going to be particle physics, and we're going to be touching on a few topics here. I guess that, probably the thing that we want to emphasize just now is that particle physics can in principle be extremely complicated. What we're going to be doing is hopefully doing a little light touch kind of whistle-stop tour through a few things, and if there are some things that we gloss over that seem extremely complicated, then don't necessarily worry about all of the details. We'll be telling you sort of which bits that you really need to understand and which you don't. Now, before we get into the material that we're actually going to be, considering and examining later and so on, I just wanted to give a very brief introduction to the sorts of physics that are done here at the University of Newcastle, just to because they really cover this range from the smallest to the largest scales, and that gives you a little bit of an idea about how some of the physics topics that you're going to cover are actually being used at the cutting edge of science. So just a couple of slides here. This one is showing some images of what's called a scanning helium microscope. This is located in the physics building just up the hill, and is basically able to image, because that's what a microscope does, objects at scales down to something like 10 to the minus 11 of a meter. And it's done using helium, because using helium makes it a non-destructive process compared to certain materials, certain samples, which you might damage by shining light onto them. So there are some images down at the bottom of what you get if you look at a shark's fin through this. So this is really looking down to some of the smallest scales that we can see, and you can image down to the molecular scales with this. So now there are other research topics that different members of staff cover, which are kind of at the nanoscale. So we're looking in the top left, there's an image there of some photoluminescent materials that have nanoparticles in them. That's why they are glowing like that. So these quantum dot nanoparticles are what you get in your QLED TVs, but they're also used for various medical applications, like you can use them to tag certain biological processes that can then help you identify those and perhaps fight disease. We've got a little schematic here of a nanomagnet. That's a magnet which is 1,000 times thinner than a human hair, and these have lots of applications as well, for example, in things like quantum computation, and also other things that you wouldn't even imagine, like self-healing paint on cars and stuff. And finally, down at the bottom is a picture of, from another one of the labs in the physics building there, of a microscope, a confocal microscope, which is then used to image molecular defects in diamonds and make them glow. Right, so lots and lots of research on things at tiny, tiny scales. My own research area is not on tiny scales, but on quite big scales, so not quite the scale of the entire universe, but I'm interested in understanding how the sun's atmosphere works and how it interacts with the Earth. So what we're looking at here is a video of a solar flare, or eruption. Let's play that again because it's just kind of pretty impressive. So this is an enormous amount of energy. This is like 1 million eruptions of Krakatoa, or like a billion kilotons of TNT. That's the amount of energy that's being released within a few minutes in the sun's atmosphere. And these eruptions drive what's called space weather. They interact with the Earth's upper atmosphere, and they can destroy satellites and disrupt GPS and so on. So there we're really looking at the largest scales. So this is just a few different topics to give you, I guess, a taste of what we're doing in physics here. Now, another thing which is useful to look at, again, before we start and really get into what we want to talk about properly, and it's becoming more and more important when we start to think about the kind of interaction between science and, like, politics and things like that. You know, vaccinations, it's like, oh, well, the scientists said that we should all do this, and then, oh, suddenly they change their minds, so, like, scientists don't know what they're talking about or whatever. And I guess the whole point of science is that it's evolving, and that it's not, there is no kind of absolute truth. So this we have to bear in mind in all the stuff that we're doing here, especially in these first couple of weeks when we're really talking about, we're going to get up to, like, things that we don't know. So is physics the absolute truth? Do we know absolutely everything? No, we don't. So in which case, what is physics, or what is science? And so then we have to understand the scientific process. So what is the scientific process? All this stuff that we're going to learn, how did we come to understand that? Well, it comes about by basically making experiments or measurements or observations of something, and then we want to try and understand that, right? So we set up a new experiment and we see something we've not seen before. So then we have to try and develop a theory that is consistent with what we've measured. And then that theory kind of leads to some model where we might try and predict, all right, so now I'm going to do a slightly different experiment. Can I predict what the answer, or, you know, what measurement I'm going to make there? And if our theory predicts well that new experiment, then that gives us some kind of confidence that, oh, then maybe that's quite a good theory. I should go on, I should keep testing that, and so on. Of course, it might be that it doesn't match with the new experiment, and so then we have to throw that theory out, or at least modify it to try to come to an understanding, kind of general understanding of how it works. So we have this kind of flow chart. We do an experiment, we make a model to understand, you know, to try to understand in general what's going on. That allows us to make predictions. We can now do another experiment. Then we have to check, does our new experiment agree with what we see? If it does, yes, great, but we do another experiment, otherwise we change the model. So what this means is that, I mean, ultimately you could never prove, because you would have to do experiments forever, you could never really kind of fundamentally prove something, but we just have to keep on testing, and so, you know, it can always be that we do some new experiment that doesn't quite fit with our current understanding, and then we have to modify it. And that's why science has evolved over the years and centuries, and why sometimes scientists do change their minds. And that's because they do another experiment, they get more data, they're able to develop a better theory, right? All right. So everything that we're going to talk about is a picture to understand the world, which is based on this idea of kind of a side-by-side development of our theoretical understanding with new experiments and developing those new measurements. Right. So with all that said, we're now ready to actually start talking about what we want to talk about this week, which is particle physics. And so we're going to be talking lots about these particles and about what our current understanding is of what the fundamental particles are and how they interact with each other. And then a lot of this has been developed through either theoretical modeling or experiments, like we said. So what are some of those experiments, and how do you do experiments on particles? Well, typically we'd like to get particles to very high energies, and some of the images that we saw earlier were of the particle accelerator at CERN, that again some of you may be familiar with. That gets particles to extremely high energies, and works kind of is roughly aligned with how the synchrotron at the bottom works. Now, the other thing that maybe you've seen before is like a Van de Graaff generator, one of these things where you put your hands on it and your hair stands on end. This Van de Graaff accelerator works in the following way, by basically building up a static charge onto this conveyor belt thing, which then charges the sphere that's sitting over the top. Now, this can produce like a big static potential difference, but it doesn't actually create fast particles. And typically what we want to do experiments is we want to get particles moving very fast, and then we want to smash them into one another. So then another thing you can do is use a so-called cyclotron. So a cyclotron works if you have an electrically charged particle, because electrically charged particles, it turns out, move in a circular motion in a magnetic field. So the cyclotron configuration looks like this, with a magnetic field pointing, as it's shown here, vertically. If you start the particle moving, its path will be bent in that magnetic field. Now, there's a voltage placed across these two, there's a gap between these two kind of D-shaped magnets here. If you flick that voltage, the sign of that voltage, at the right speed, you will get the particle to increase its speed every time it jumps from one side to the other. Now, the problem is that every time it jumps from one side to the other, the radius of that circular motion increases, because the radius is proportional to the speed that the particle moves. So either you need a gigantic magnet or a gigantic experiment, or you're kind of limited to the actual speed that you can get the particle to move. Now that's where the synchrotron comes in then. In a synchrotron, it's just a giant tunnel under the ground. You want the particles to go round and round and round, and to get gradually faster and faster and faster. And in order to do that, you need to get your magnetic field to be increasing, because that also affects the radius that the particles are moving at. So typically these things are enormous, and then we're going to see in particular the particle accelerator at CERN. That's why this is so big. It's because there's a limit to the size of the magnetic field that we can actually create, and that limits how small a radius we could make for the motion of this particle. Right, I should say that you don't need to understand these details here. It's not critical exactly how these things work. It's just the kind of principle of how we make them. Now, so we're going to be doing experiments, and we're going to be accelerating particles, trying to make them go faster and faster and faster, and smash them into each other to see what comes out. Now, as we go through the lectures, I'm going to be doing some Kahoot quizzes as we go through. Hopefully that kind of helps to keep you guys awake. Obviously, you don't have to play along, but hopefully people want to play along. When I told my eldest daughter, who's 14, that I was doing Kahoots in the lectures, she asked if the students go like absolutely crazy and love it. Because apparently that's what happened to her school. I had to break it to her that students really didn't go crazy with enthusiasm, but I don't know, hopefully it keeps you awake a little bit.
Yeah, look, I did it overnight last night.
Yeah. So that's all right. I'm not expecting, but let's have a go anyway. So we'll do some quizzes. I think there's only a couple of questions today, but we'll have some more as we go through. And yeah. So let's see. I'll wait to till the names start popping up, and then we'll start with our first question. First question's a little bit of a nasty one because we haven't really said what the answer is to this actually. But it's a case of just having a guess and seeing what you think. What is the advantage of using colliding beams in a particle?
Yeah, it's cool.
What? Where are the answers?
Alright, answer is always C.
Where are the answers? What? Yeah, that's not good, is it?
And you've only got 2 questions in there too.
Where's that? Oh man.
No!
What does the second one have? Oh, I don't know. We don't. What is the next question? Well, this is a bit of a disaster, isn't it, really? Oh, well done, Emily. There we go. Does this one have the actual... Come on. Oh, right, okay, I gotta figure out where the answers are.
I'm gonna say it's gotta be 6.
Yeah. Right, how do I get back? Now everybody knows what the answers are. Well, that was a bit of a disaster. I'm like massively jet lagged, that's my excuse, but where are the questions? All right, okay. Oh, we'll figure it out. For the next lecture, there will actually be answers to choose from. But well done, Ben, I suppose. There we go. Oh well, kind of spoiled our Kahoot fun this time, didn't it?
I think that's actually the best Kahoot I've ever been a part of.
Yeah, excellent.
Yeah.
Right. So then once we've accelerated particles, so what we were supposed to learn from that first question was, so why is it relevant, or why would you want to have 2 beams of particles moving in opposite directions? It's basically because you get twice the amount of energy. You get twice the total kinetic energy when the 2 particles hit each other, because the 2 particles are moving in opposite directions rather than just having one particle smash into something that's stationary. Now eventually we smash these particles into each other with the idea being that they kind of explode and we can see all the bits that they're made of. And then you've got to figure out, well, how do you actually detect all the bits that come out? So again, there are various different ways to do that, and from top to bottom is sort of, I guess, the kind of historical development of how that happened. So initially, the first detectors were just using like a photographic emulsion, where when the particle went through, it created a chemical change that you could then see. And then there are various different technologies now that allow us to detect the passage of those particles through. So you want to smash 2 particles together, a whole load of stuff comes out, and you want to somehow detect that stuff that's coming out. So one option is to use a cloud chamber. So a cloud chamber contains a vapor, and then when a particle goes through, it causes like a condensation of the material, and you see the condensation tracks. A bubble chamber is a little bit similar, except that you've got a liquid now. It's close to its boiling point. Again, when particles pass through it, it creates a trail of little bubbles, which you might detect. But then the more modern detectors actually contain like a whole bunch of wires, basically, which where a charged or ionized particle will pass through and create like currents along all those little wires, and by looking at where the currents were formed, you can reconstruct where the particles went. Again, detail's not that important, but there are basically these various different technologies that have been developed to see where all the particles go. So like I said, CERN is one of the most kind of famous and successful so far particle detectors. This is it's a gigantic tunnel under the ground. It's a circle because our particles will move in a circle in this magnetic field. It's gigantic because the bigger it is, the faster we can get the particles to go for a fixed value of the magnetic field. And we can accelerate particles to enormous energies. So we're going to be seeing energies in this slightly weird unit of electron volts as we go through. This is 14 tera electron volts. Tera is 10 to the 12, 10 to the 12 or 10 to the 50? 9 would be giga, 6 would be kilo, no, 3 would be kilo, 10 to the 6 would be mega, 10 to the 9 would be giga. I think 10 to the 12 is tera. So 14 times 10 to the 12 electron volts. Now, it's not very big energy. The energy of 14 flying mosquitoes, which we don't have to worry about now, but maybe later in the semester. Yeah. But it would depend. Yeah, exactly. Mosquitoes here are a bit bigger, right? But the masses of the particles are so tiny, this is at enormous speed. And it's the highest energy density produced in the laboratory, which sort of goes back to like the conditions of the early universe, and again we'll talk about that as we go through. So to get an idea of how fast the particles are going, it's a 27-kilometer ring, and the particles travel around it 11,000 times per second. So they're going pretty quickly, and they smash into one another, and then we've got to figure out what comes out. Right, so that's what we do with these experiments. So the other thing that we're going to talk about today is about forces and how we can understand the forces between the particles. And in particular, we'll talk about the strong nuclear force. So by around the 1930s, we knew that the nucleus of atoms contains protons and neutrons. But then there's a question of why. So we know that charged particles, if they've got the same charge, should repel each other, right? Two positive charges should push away, whereas negative and positive should attract. So then there's the question of, well, how are all these positively charged protons held together in the nucleus? Why doesn't a nucleus just fly apart? Because the protons should, and in fact do, repel each other by the electromagnetic force. So then it had to be proposed that there was some additional force which held the protons in the nucleus and held the nucleus together. Now, the only other thing that we really know about it then, on that basis, is that it has to be stronger than the electromagnetic force, which is trying to push the particles away. So if it's a force that's in the nucleus and it's strong, then why don't we call it the strong nuclear force? So that's what this is called, the strong nuclear force. So then how do we understand how that strong nuclear force works? Well, forces in general, we can think about the idea of a force field. So for example, are maybe kind of familiar with the idea that you would have an electromagnetic field around an electrically charged particle, and that, you know, usually you draw kind of little arrows about, you know, what that field does. Maybe for like a magnet and a magnetic field you did back in primary school, you had your magnet and your iron filings, right? And you put the magnet underneath and the iron filings all kind of line up in a pattern, and that kind of shows you the shape of that field. But so then the force between, say, two electrons, the repulsive force between these two electrons here, is associated with that electric field. Now we have to kind of borrow a little bit from next year, and we have to kind of make a little jump of logic, because the electric field, the actual propagation of an electric field is by an electromagnetic wave. That's like what a time-dependent variation in the electric field would correspond to. And then electromagnetic waves are also light, or light is one part of the electromagnetic spectrum. Maybe you heard about that before. We do cover it in much more detail later. And then we know that light is also, we can think of as a collection of photons. So this is, now we start to get into some of this kind of tricky stuff when you talk about physics on very small scales. And again, we're not diving into the details, but we can think about then this interaction between these two electrons. If it's associated with the electric field, which is associated with electromagnetic waves, which are, you know, we can describe in terms of photons, then we could also think about that force between the two electrons as being associated with photons. And in particular, we kind of think about it as like one electron is kind of passing a photon to the other electron. So now, again, why would this create a force, or would that be a useful way to think about a force as kind of particles exchanging some kind of other force-carrying particle? So the really crude analogy is usually drawn with like kids on roller skates, and the way to think about it is that you imagine that, you know, if you have these two kids on the roller skates and they're throwing some objects to each other, then there will be some kind of, the kids are going to be pushed away from each other, right, due to the momentum of like the pillow that they're throwing or whatever it is. Then another way that force might work is if both the children are trying to grab the pillow, then they will move towards one another. So obviously, if we've got two electrons, and if it's a repulsive force, then it's more like they're throwing the photon backwards and forwards, and that gradually pushes them away. So in this way, we kind of exchange energy and momentum between the two particles by exchanging some other particle. So now we imagine this is known to be a photon in the case of the electromagnetic force. So the electromagnetic force is kind of carried by photons. The photon, though, is a virtual particle because this process is too fast to be observed by any measurement. So the particle, now we start to get into kind of really complicated and slightly mind-bending stuff, but it's a particle that doesn't really exist. It's like a virtual particle. So then the thought was, anyway, if we kind of, let's just skate on and see where we get to. The thought was, well, maybe all forces can be modeled as some kind of exchange of virtual particles. And so again, we're getting back now to this force that holds the particles in a nucleus. The idea was all these protons and neutrons are sitting there and they're exchanging virtual particles, which creates a force that holds them all together. And the virtual particle was called a meson. And so then then some theory was developed to try to understand, well, what is this meson, and what are its properties? Now, we're going to do a little example here. If we can switch over to our document camera. Now, photons don't have any mass, but it was assumed that the meson does have some mass, and that means that the strong force only acts, this strong nuclear force that holds the particles in the nucleus only acts over some short range. So we've now got this theory where we create a virtual particle out of nowhere, pass it from one of our nucleons to the other one, and that creates the force. Unfortunately, that violates the conservation of energy. That's one of the kind of fundamental principles of physics, is that you can't create or destroy energy. But it turns out that if you go to very, very small scales, then we can borrow this equation here from quantum mechanics, which tells us that we can create energy so long as we only create it for a very, very short time. In particular, we can create an amount of energy delta E for a time delta t, so long as the product of those things is less than or equal to h over 2 pi. And h is Planck's constant. So we're now being asked to calculate what the mass of this meson is. Right, so what we're going to do is we're going to assume that we have our virtual particle is moving very, very fast. So we're going to assume that its speed is roughly the speed of light. And we're also going to use the maximum distance that we want that particle to travel. So that maximum distance that a particle can travel, well, the distance is just the speed times the time, so just v times delta t. And then we're saying that the particle moves at a speed c, the speed of light, so our distance that our particle could move in that time is just c times delta t. And we're going to call that equation 1. And then, so that's going to give us something associated with the delta t in our yellow boxed equation. And then we need to know what to do for the energy, delta E. Now, again, we're going to talk about this more in the coming lectures, but there's an energy associated with just the existence of a particle, and that's called its rest mass energy. Now, probably E equals mc squared is an equation that you've heard before. This is just the relation between the energy of a particle and its mass, so the rest mass energy. So then all we do is we substitute these two expressions, into the equation in the yellow box. So we've got delta E times delta T. Well, that's m naught c squared for the delta E. And then we can rearrange equation 1 to get delta T as d over c. And we're told that that has to be like this twiddly thing here means of the order. It's basically, it's like approximately equal to. Or m naught c squared is of the order of h times c over 2 pi d. So this the m naught, that was the mass of that virtual particle. That's what we're being asked to find. So c is a constant that we know, and h is a constant that we know, but d is the problem. But we know that that this force has to act over the nucleus. So let's take d to be the size of a nucleus. Now again, we have to kind of appeal to some experiment to know what the size of a nucleus is. Typical size of a nucleus is this number here, 1.5 times 10 to the minus 15 meters. And so finally we're ready to substitute in, and we can calculate what m naught c squared is. That would be 6, so h, which is 6.63 times 10 to the minus 34, times c, which is 3 times 10 to the 8. We can divide by 2 pi times our 1.5 times 10 to the minus 15, and we'll get 2.1 times 10 to the minus 11 joules. So a very, very tiny number in terms of the kind of units of energy that we expect, that we're used to using. And we can then, what we typically do is to convert that into a kind of more convenient unit of energy. And so we mentioned this thing electron volts before. An electron volt is just defined as 1.6 times 10 to the minus 19 joules. So that's just a definition. So if we divide the number that we've got, 1.3, if we divide this 2.1 times 10 to the minus 11 by our definition, by our 1.6 times 10 to the minus 19, that gets us an answer of 1.3 times 10 to the 8 electron volts. Or we were asked for the mass, not the m naught c squared. So 1.3 times 10 to the 8 electron volts, divided by c squared, which again looks like a really weird unit of mass, but we'll talk more about why we might use that. It's basically because the numbers are so ridiculously small when you talk about masses. To use kilograms would be crazy, your numbers would be tiny. Okay, so the solutions when they go up, the slides when they go up will have the answer to that in case you didn't quite get the last thing. So this is our final slide. It turns out that we have a different understanding now of how the forces act, and we'll talk more about that later. But basically there are 4 fundamental forces that are the strong force that we just mentioned, electromagnetic. There's a weak nuclear force and gravity as well. So kind of the goals of particle physics are really to figure out what all the particles are and how these forces act between them. And we'll explore that more in the remaining lectures this week. So for now, let's wrap up and we'll pick it up there in the second lecture. Sorry, lecture before me ran over, and then we're sort of fighting to catch up. Right. Right. Yeah, should be all logged out.